Hello everyone. Today we'll talk about the solution to the problem minimum time to visit a cell in a grid. This problem is quite similar to yesterday's problem, so if you haven't watched the video for that, feel free to do so. Again, of course, we have a grid. We are going from the upper left corner to the bottom right corner. In this case, it can be impossible. And what we essentially care about is we can only enter a given cell. Entering a cell costs always a second. But we can only enter a cell after enough time has passed. And at every point in time, we have to make a move. Up, down, left or right, but we have to make a move. This fact that we are forced to make a move is not very important for the solution, but it makes it a little bit more tricky. But it's mostly just details. So, we know that to solve a problem using something like Dijkstra's algorithm, then we want to have this nice greedy way of trying to surmise what is the easiest way, the fastest way to enter a node. And in this case, of course, we want to enter a node in time that's either the minimum time for that node, because it's impossible to do anything better, or from some other node that is its neighbor, and for which we know that we already know the shortest path. We want to enter it from that node as quickly as possible. So if it wasn't for the requirement for always making a move, just entering from a different node as quickly as possible would be taking the time for the previous node and adding 1. Right? So if our node here requires v and the node here requires t, then we can either take v or we can take t plus 1. We have to take maximum of those two, because of course we have to get into v through t. Maybe there will be some other way, but t to v requires at least v time and at least t plus 1 time. And here the problem of always making a move comes up a bit, because it's not just t plus 1, but through the standard checkerboard pattern, checkerboard argument, because we know that when we look at a checkerboard, like a chessboard, we might imagine that whenever we are on a cell that's white, the number of seconds that have passed is even, because we start with 0 here. And whenever we are on a black square, the time that passed is odd. And it's easy to see why, because whenever we make a move, we either move from white to black or from black to white, which means that the parity always flips. So we cannot just spend time t to get to this node, and then spend time t plus 1 to get to this node, if v, so essentially when v constrains us, we have to make sure that the parity is correct compared with the parity that we have here. Or in other words, for instance, we have made an even number of steps here, and v is even. That means that we cannot enter the cell here at time v, we have to enter it at time v plus 1, which is the next odd number that's at least equal to v. So this is the first detail where this always make a move comes into play, and I can already go over the second detail, and that second detail is that we might be stuck on the initial spot. Because notice that if there is any move that we can make, then we can just go back and forth between two cells and pass the time, wait however long we want, so then we'll reach the cell. However, if at the very beginning we cannot make a move, so if those two values that are right next to the starting cell are both greater than 1, we have to return -1, and this is a check that we should just explicitly specify at the beginning. Okay, so we can look over the whole solution. Here's standard boilerplate. Of course, we'll be maintaining for the Dijkstra's algorithm a priority queue. So we're starting at time 0 at position 0, 0. We go over the whole priority queue and we take the node from the top. Now, if that node is the final node, then we can return the answer. If we have already processed this node, we don't want to process it again, so we continue, because that means that we have already processed it before, and that means that we found a shorter path to it, so we don't want to process it. And of course, now we're processing it so we can add it to the set of visited nodes. For every direction, we try to go in that direction. So row plus difference in rows, C column plus difference in column. We have to be inbounds and not have that tile be visited, because if either of those is true, then we continue. Otherwise, we push the new value for the position new row, new column to our heap. And what is this new value? Well, it's either v plus 1 or the time that we have here plus 1. And we have to correct for what if v and the minimal required time. So I guess the letters I've used here were not very useful, or rather might be a bit misleading, because in this case v is actually the value that we had here, so this is t. That's why t plus 1 is here. And this is the value from the cell, and we have to sometimes add 1. So or in this case, we add 1 and sometimes subtract 1. But we have to sometimes add 1, we have to add 1 if the parity is not correct. And at the end we can return -1 to make sure that we always return something, because we have to return the value. So we have here used a standard greedy Dijkstra-like approach, and this part gave some tricky portions that we must move. And otherwise the idea was pretty simple for us to just imagine that we can just move back and forth, so essentially we just can almost always and almost precisely visit every cell. We can quite easily determine the time of the first visit for every cell, like in normal Dijkstra.